Yeah, I hope Christ is with you, and those of you that are of faith, I hope your faith is stronger than it was yesterday, and those of you that aren't, come to Christ. He's an eternal winner, and uh, people always say like, "I'll find a way." Like, I don't mean to be cynical. You won't find a way because there's only one way, and the only way is the Christ. Okay, and to those of you, the goons of the enemy, what's a kosher way to say this? Like, every time I read my Bible, Jesus talking about like how you dug yourself a pit and you're gonna fall in it or whatever. Make sure it's like really deep and like fall and don't ever come back so that the rest of us can live in harmony and peace. All right, let's get started. So this is pretty cool. The golden ratio, right? So that there are like what is it? Like a number of super important math numbers, right? And so like, 0 and 1 obviously, but like pi and e, and like the most beautiful number in math is what they call this. Um the golden ratio, right? Phi, and perhaps because it appears everywhere in nature, but like I would rank it as the fifth most important number. Actually, the sixth. Well, we don't like six, so the seventh. Fifth being I, the imaginary unit, not me. Okay, cool. So here's the quintessential way of seeing how the golden ratio like could be like gotten to in math, right? And so this is the so-called golden rectangle. What you do is like you take a rectangle. It doesn't have to be x by 1, quite frankly. It could be any rectangle, and you divide it into two parts or two polygons, or one of them is a square and the other is a rectangle. So we do that in this manner. So I took the what I assume to be the shorter side, according to my visual, the 1, and made a 1 by 1 square. Clearly this is still 1 and this is 1, so this square here is a 1 by 1. So the other way to do this is to start with a square, right? And then like extend the square to be a rectangle. But this is done very precisely, like if it's a square that you start with. The construction is that you start with the midpoint of a side of the square, say this here, and you draw a line to this corner, and that forms a radius of a circle that's centered here, and you swing the circle like, let's say, counterclockwise, and you land here, and therefore this is how you know how far to extend the original square that you're going to turn into a rectangle. The point is, you can start with a rectangle, turn it into a square and a rectangle, or start with a square and turn it into a square and a rectangle. And either way, what ends up happening is you end up having two similar rectangles. And the two similar rectangles are the original one that we started with, in this case the x by 1 rectangle. I'm going a little too fast. So the two similar rectangles are the x by 1 rectangle, the big one, and then the now smaller rectangle that's formed here. Those two rectangles are similar. And the only thing that I displayed in this visual that was not present is letting you know that since its whole side is x, if this is 1, this has got to be x minus 1 clearly, right? Okay, cool. So then now when we put proportions equal based on the similarity of the rectangles we already mentioned are similar, this is what we'd have to write. And this is a simple rational equation that we can solve using the quadratic formula by first cross multiplying and seeing that it leads to a quadratic, and the quadratic is this, right? Okay, cool. Now, as this is not a factorable quadratic, we enlist the help of the quadratic formula, wherein we write this, right? That's simple substitution. So, yeah. All right. And then that reduces this here, this expression, plugged into the quadratic formula reduces to this. Now, we know the quadratic formula always leads to two numbers, right? One's with a plus and the other with a minus. Whether you see it as minus, plus or minus, doesn't matter. And the one that we want is the positive number. And that's 1 plus square root of 5 over 2, right? And that is phi. That's the value, the exact value of phi. Because, like, well, this is approximation. Anytime we enter decimals for a number that has non-terminating decimals, then there is no decimal approximation that's exact. This is the exact number, right? Okay. Now, we know that the minus would lead to a negative number because the square root of 5 is roughly 2.23, and 1 minus that is going to give us a negative. Anyway, so we know we don't want um, the negative value. And so we keep the positive value. Now, is there anything more profound to say that like you could get to this golden ratio, phi, through this little derivation? Well, yeah, there's something like more profound. And of course, the fact that it exists in nature. The spiral, the golden spiral. By the way, before I go on, like, so you'd continue this process and turn this rectangle into a square, and a rectangle that isn't, and the rectangle will be in turn similar to the original rectangle and this one here, and you keep repeating that process, and you draw a spiral going through like where, you know, this line was formed. There will be a line formed here, so you draw a spiral going in that manner, and that's how you form the golden spiral, which is what's seen in nature. Golden ratio, golden rectangle, golden spiral, right? Okay, but let's carry on and see what it is that I'm, you know, I have left to reveal that is like supposedly profound. And this is what I have left to reveal that's supposedly profound. So erect a vertical axis and draw a horizontal line that's golden, so as to mark the intersection with phi, right? And so like I'm saying, like this is like kind of like the y-axis, and there's some horizontal line that we draw which marks where along the y-axis the golden ratio phi would lie, right? And so that's right there at the intersection. Now, I have a number of videos on the Fibonacci sequence, and so you could watch those, but we know that the Fibonacci sequence, darn Fibonacci, I wish I was around back then when I could have just listed 1 and 1 and added them, and then added the previous 2, and that's all I needed for my legacy and my name to live forever. Okay, no, just kidding. I don't really care. I'm all about Christ and promoting Him. Okay, anyway, there, the Fibonacci sequence is there, right? Now, so if you take the next number over the previous, the first ratio in the Fibonacci sequence, quotient, let's say, so as to not confuse. Alright. And anyway, the first quotient we can write if we take the next number over the previous in the Fibonacci sequence is 1 over 1, then 2 over 1, then 3 over 2, then 5 over 3, blah, 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 right? Okay, let's write them down. They look like this, and I also wrote down the approximate values. This is exact, as you know, circling back to what I was saying, because, well, the decimal terminates. This is an approximation because the decimal never terminates, but you get it. Now, pay attention to the values of what we get when we do, again, the next term over the previous in the Fibonacci without skipping. We get these, and of course we can continue, but this suffices to illustrate what I'm trying to illustrate. Now, look. So, the first quotient, 1 over 1, of the Fibonacci sequence next number over the previous, is going to land on our vertical axis below the value of phi, right? And then the next quotient, 2 over 1, is going to lie above it and symmetrically, like, you know, the same vertical distance from this golden line, right? We just made up a new thing. It's called the golden line. Anyway, then we continue, look, and so the next ratio is going to come on this other side. 1.5 is below 1.618, which is the approximate value of phi, right? Approximated to 3 decimal places. You get it? Are you seeing this? Isn't this cool? And next, the next ratio, or rather quotient, next term over the previous from the Fibo, is going to go on the other side. And then this side. No, wait, that's supposed to be done slowly, but whatever. You get it. So there, and then there, and finally there. And maybe one more? No, that's it. You see this? What happens is, if we keep doing the next term over the previous term in the Fibonacci sequence, and look at those quotients, they're going to give us finer and finer, that is better and better approximations of phi. So that in theory, at infinity, like, right, very far off to the right in the Fibonacci sequence, we're going to, like, match it in theory, right? Isn't that cool? Well, not as cool as Jesus, but pretty cool. Have a wonderful day. Take care.